Good afternoon, everybody. I am Abhiram, a master student at RWTH Aachen University, collaborated with Aerodynamisches Institute Aachen and Jülich Research Center under the guidance of Mario Rutgers and respective head of institutes Professor Wolfgang Schroeder and Dr. Andreas Lindemann. Today, I would like to present on shape optimization of respiratory flows through reinforcement learning. The very need for shape optimization in respiratory flows arise due to the presence of deviated septum in nasal airways which cause breathing problems. Even after undergoing a septoplasty surgery, only 56% of the patients are satisfied. Here, the two main functionalities of the nose are addressed to, that is, proper supply of air which is related to the optimal pressure loss and heating of air during inhalation. Hence, the main goal of this shape optimization is to take into account these fluid mechanical properties and produce the optimal shape of the nasal airways to maintain the main functionalities of the nose. There are three different approaches to solve this problem. First one being the use of 3D printed nose. This is an experimental technique where sections of 3D printed nose are assembled and flow through these nasal cavities are analyzed. The main downside of this approach is that the 3D printed model can only be used once. The next approach is to perform virtual surgery. Here, the beginning virtual model of the nose is obtained from an initial CT scan. The shape of the nose is modified virtually. The simulations are run for each modification and the pressure loss is compared with each other. In this approach, it is difficult to reach an optimal shape. Hence, another more robust technique is to utilize machine learning, especially reinforcement learning. In this technique, CFD simulations are run in feedback loop with the artificial neural network and different reinforcement learning algorithms. After every simulation, the optimum is targeted based on the actions performed taken by the algorithm, and the weights of the neural network are updated accordingly. Hence, a good optimal shape is obtained. The main difficulties in this approach is that a proper optimal criterion and an action space should be defined. This technique forms the main essence of this presentation. Since nasal cavities are complex three-dimensional geometries, the computational domain is simplified into a narrow two-dimensional channel with a bump at the center to depict the deviated septum for our current study. The CFD simulations are performed using an automated grid generator and thermal lattice Boltzmann solver. We see that as the bump radius increases, the pressure loss increases and temperature ratio for an arbitrary value is reached earlier. This shows that the pressure loss and temperature have competing goals and compromise needs to be found. A brief idea of agent-environment interactions in reinforcement learning is introduced here. The agent receives an observation from the environment and performs an action. This results in the state of the environment to transition to the next time step. Based on the action performed, the agent receives a reward or a penalty. The main difference between the on-policy and off-policy methods is that the off-policy methods the agent learns the optimal policy with the help of greedy policy and behaves using the policies of other agents. That is, it has two policies, the updating policy and the behavior policy, whereas the on-policy methods improve the policy that is used to make decisions. The actor-critic method is a combination of both policy-based and value-based methods, in which the actor network returns the probability distributions of actions and tells the agent what action to take, and the critic network allows us to understand how good these actions were and returns a value output. The policy gradient methods target at modeling and optimizing the policy directly. The A to C and PPO are compared to a baseline case performed with the so-called reinforce algorithm. The reinforce algorithm is the simplest of the policy gradient algorithms, where a single neural network is used to update its weights without the aid of another network to give the quality of the actions that it took. As explained in the previous slide, the the single-agent training for our application is depicted. The computational domain, with the two main functionalities of the simplified nasal cavity, forms the environment. The normalized pressure and temperature from the CFD simulations and the bump radius are given as observations to the agent. The agent performs an action by changing the bump radius and sends this action back to the environment where the CFD simulations are run again with the new radius. For the action performed by the agent, it receives a reward. This reward depends on whether the agent was able to meet the reference radius or at least enter the target zone as depicted. The reward is scaled by a factor of 5 for better learning of the agent. The future rewards are computed as the rewards to go, including the discount factor, which accounts for the penalty to the uncertainty of the future rewards. Here, the results for the single-agent training with the PPO, A to C, and reinforced algorithms are discussed. It is clearly seen that the reinforced algorithm does not meet the optimal or the reference radius, whereas the A to C and PPO algorithms are very close to the reference radius. This reference radius was determined by running simulations for all possible radii in steps of 0.1. This can also be seen in the table of results where the A to C and PPO have reached the target zone in about 90% of the batches. A study of hyperparameter tuning for parameters such as learning rate and number of updates of the weights of the neural network was performed on the A to C algorithm, and the changes in the clipping region was performed on the PPO algorithm. All these studies resulted in a similar efficiency of the A to C and PPO algorithms. Hence, both need to be investigated in more complex setups. Moving on, a multi-agent version of the PPO algorithm was trained on two overlapping bumps in the computational domain. A decentralized training technique was utilized here. Initially, the difference in the normalized pressure and temperature was used as an optimality criteria for the single-agent training. Extending the same criteria to the multi-agent version results in a number of optimal values or combinations of radii. Hence, a new optimality condition was developed by maximizing the sum of the normalized pressure and temperature as depicted. This resulted in a single optimal radii combination comparatively decentralized. MAPPO reached the best radii combination under the error of 1% after 76 batches. To summarize, shapes can be optimized by considering fluid mechanical properties, but the decision-making process related to this needs improvement. The main properties chosen for this study are pressure loss and temperature increase. A simplified two-dimensional version of the three-dimensional nasal cavity can be used. The PPO and A to C algorithms are successfully trained to modify perturbations. The complexity of the problem will be successively increased and will be applied to the nasal cavity soon.